So another set of reviewing, so this is class notes number 2, but these are a number of things, right? We kind of been talking about ways to make alcohols, and we started out talking about Grignards and carbonyls, and organolithiums and carbonyls, right? Carbonyls are ketones, aldehydes, esters, amides, carboxylic acid, C-derivados. We talked about hydrides, H- reacting, but here's a number of things that you learned last semester on ways to make alcohols. And a lot of these involve, the classic kind of examples. Your classic SN2 type reaction, right? You take an alkyl halide and turn it into an alcohol. SN1, where you have some sort of leaving group in usually acidic conditions or water, right? And you get in water and you get an alcohol that way. You learned about alkenes reacting with H plus and then water adding, making it through a carbocation intermediate, right? That's an addition, right? Substitutions, additions. You learned about hydroboration oxidation. Now we're showing some stereochemistry here, right? How does boron react with an alkene? And where does the boron go? Where does the OH end up? And are things on the same side or the opposite side, right? Where do things end up together? You learned about mercury, right? Which gives the Markovnikov product. So a borohydride gives the anti-Markovnikov product, which is just a fancy Russian way of saying, where does the OH end up? Anti-Markovnikov, less substituted part of the alkene. Markovnikov, more substituted. It's just looking at the products. Where does the group end up? Anti, less substituted. Mark, more substituted. Mark, more. Mark, more. Markovnikov, more. More substituted. BR2, that's the example I'm going to show you. I'll send that to you video. BR2 in water can also get alcohols. This is the one that's very similar to the epoxides, where you get that trans addition. I think this is actually incorrect. This OH should be hatched because the boron adds in a syn fashion. So if it added the H to the bottom, it added the OH to the bottom as well. So that's a little mistake they have made there. We just got done talking about Grignards, right? Ketones, Grignards, aldehydes, ketones, esters can make alcohols as well. So you should review these. This we just did. Hydride reagents, hydrides, right? Lithium aluminum hydride, sodium borohydride are 2 H- sources. If it's a ketone or aldehyde, we can use either one. If it's an ester or carboxylic acid, only lithium aluminum hydride works. Right? Notice what they make them both into primary alcohols. But we need the more reactive hydride for the less reactive carbonyls. How about this example? This you've seen. This is taking into account if you see a terminal alkyne, you know that's acidic, right? Because of sp hybridized, stabilizing the negative charge, close to the positively charged nucleus, smaller hybrid orbital. And if you react it with Na plus, NH2 minus, NH2 minus is a really strong base. Right? What's that going to do? It's going to take off that H. You're going to get that acetylide. That's a good nucleophile, right? You've seen that, or you could use Grignards, right? This is another example of C minus. Grignards or organolithiums do that. The C minus could add in, open that up, make a tetrahedral intermediate, and you can get this type of alcohol as well. So same difference, right? Same difference. Just type of nucleophile. So now we have a new electrophile. We've been talking a lot about different types of nucleophiles. Grignard, organolithium, the acetylide, the C minus alkyne, the hydrides. Now we're kind of introducing a new electrophile, an epoxide. If we have a strong nucleophile, these are considered the basic conditions. Things react at the less substituted carbon of the epoxide. Acidic conditions react at the more substituted. So new electrophile, different types of conditions, different types of regioselectivity. And all we're doing now is, okay, here's a bunch of nucleophiles. That's all these are. C minus, Cn minus, H minus, S minus, O minus. Okay, we're just changing the nucleophile. It's all going to the same spot. It's adding here and breaking that bond. So you get a whole mixture of products, but it's the same mechanism over and over and over again. It's the same mechanism, just different nucleophiles. All we've changed here is the nucleophile. Before we all used carbonyls, and all we changed was the nucleophile. Again, right? So, if it's acidic conditions, here's some opportunities for acidic conditions. They're always going to be given away by H+, or HX. And HX means, what does HX mean? That means HCl, HBr, or HI, which is strong acidic conditions, right? Those are reactive acids. So you just treat that like H+, I-, H+, Br-, H+, Cl-. And the first step in those reactions is you actually protonate the epoxide. The epoxide oxygen gets protonated to make it more reactive, right? Because this is an electrophile. H+, HCl, these are all electrophiles. That means your epoxide is actually going to be the nucleophile in the first step. Okay? And of course, it doesn't go through a carbocation. That's why you still get trans addition no matter basic or acidic. No carbocations with epoxides. Don't have them. Don't do it. Just like bromonium ions, just like the Br2, the bromonium ions.